Welcome to this episode of Mr. Lehman's Knowledge Explosion. In Lesson 1 of Unit 8, we're going to be talking about similar right triangles. But the similar right triangles we're going to be talking about are created when we take a right triangle, such as the one I have drawn up here at the top, and we draw an altitude from the top to the hypotenuse of that right triangle. So what I have is drawn ABC and drawn the altitude from point B down to D. Now, definition of altitude means it's going to make a right angle. And you'll notice that we get three different triangles when we do that. We get ADB, we also get BCD, and then we have the original triangle that we started with, which was ABC. So when you look at them overlapping like this, it can be difficult. So what I've done is I've drawn all three triangles in the same direction so that we can compare them. And what we notice is they look like they're the exact same triangle, only different sizes. And what we call that is similarity. So to be similar, you need two things. You need the angles to be identical, and you need the sides to be in proportion. So what we have here is angle A matches angle A in the big triangle, and the 90-degree angles match, which means by default angle B and angle C in the smallest triangle and the biggest triangle have to match. So that fits our definition of similar. If all the angles are congruent, those are similar triangles, and the big triangle is either twice as big or 3 times as big or 4 times as big for each side. We don't know because we don't have those numbers, but those are similar. So this symbol here means similar to. So we're going to write the statement that says triangle ABC, the biggest of the triangles, is similar to triangle ADB, the smallest of the triangles. And we're going to do a similar process for the middle triangle that I have drawn here in red. Angle C is the same as angle C because that angle never really got changed. And the 90-degree angles are the same, which means angle B has to be the same as angle A in that biggest triangle because you only get 180 degrees total, and if two angles match, the third ones have to be the same because they're the leftover part of that 180 degrees. So I can now say that that middle triangle, BDC, is also similar to that biggest triangle that I started with, ABC. But if ABC is similar to ADB, and ABC is also similar to BDC, we can cut out that middleman and say ADB has to be similar to that second triangle, BDC. So the main thing we need to understand here is when you draw the altitude to a hypotenuse, then the two triangles that you create are going to be similar to the original triangle that you started with and to each other. Which means when you turn the page of your workbook, you're going to see something like this. So here I've drawn all three triangles again, but we're going to take the side length now and look at them. Now I'm using variables to show that this could be any set of numbers that you want. We're going to take those side lengths, A, B, C, D, and E, and we're going to put them onto the triangles in the right places. For example, A is segment AB. So AB would be here. But it's also over here. That segment AB is a hypotenuse and a leg at the same time. And that's what can make this difficult at times. You need to look at it as both, depending on which triangle you're looking at. Side C would be from B to C. That would be side C, so I see BC over here, and I also see BC over here. So that's going to be labeled as C on those two triangles. And then we have segment B, which was the altitude, that's from B to D, which is the altitude and a leg at the same time. So that's going to be B and B. So what you need to see is all these overlapping pieces that share the same number. And then AD was D, that was just part of the hypotenuse, and then CD we labeled as E, that was the other part of the hypotenuse. So when we set up these proportions, what we notice is the same number gets used twice. So for example, if I was going to compare D to side B, B on the middle triangle, and I wanted to come back and compare B, I would have to compare it to the right side of the middle triangle, which would be E. So what we get is this proportion that says D over B equals B over E. And this relationship right here, where B is across from itself in a proportion, is called the geometric mean. And the geometric mean simply is when the same number is across from itself in that proportion. But B was something specific in this triangle. B was the altitude of this big right triangle that I started with. So that means the altitude of my triangle is the geometric mean of the two numbers D and E, which were the pieces of the hypotenuse that the altitude created. That's a lot to wrap your mind around. So on the next page I tried to put that in a nice clean theorem for you, but the words sometimes make it harder than the math. So the theorem says, in a right triangle, the altitude drawn from the right angle to the hypotenuse, so we're talking about segment B, cuts the hypotenuse into two segments, segment D and segment E. The length of that altitude is the geometric mean of the lengths of those two segments, which means it's going to fit into this proportion. But when you solve a proportion, you're always going to cross multiply and say B times B is B squared, and then D times E is D times E. So what happens is, and how I'm always going to start to say this is, the altitude squared should always equal the two parts that it created, in this case D times E. So let's look at that with some numbers. In our first example, we have to identify which of these three things is the altitude. Well, X is the line that's being drawn from a vertex to the opposite side. So that's my altitude. So this theorem says the altitude squared, so X squared, should equal the two parts that it created multiplied together. So the two parts that were created were 10 and 4. So I'm going to multiply those two things together, and that should equal my altitude squared. Now this is a very simple equation that I can solve. So I'm going to get x squared is equal to 40, so x must be equal to the square root of 40, which reduces to 2 root 10. Simple to use, a little more complicated to explain. So let's do the next example. Again, the two parts that are created by the altitude would be x and 10, and the altitude this time is 4. So don't always assume you're going to be multiplying a variable. Squaring a variable. In this case, you're going to say the altitude squared, so 4 squared, should equal the two parts, x and 10, multiplied together. So this time I get an equation that says 16 equals 10x. So when I divide that side by 10, I get x is equal to 1.6. And that's how we're going to use this theorem. So remember, the altitude squared is equal to the two parts that it created multiplied together. And if you can believe it, that's the easy of the two theorems. If you turn the page, you'll find that I've drawn the same three triangles, and I put those side lengths on all three triangles. And now we're going to do another relationship of geometric mean. So I'm going to set up a proportion. Let's say I want to compare the small triangle's bottom side D to the largest triangle's bottom side A. And then I want to compare the hypotenuse of A to the hypotenuse of the large triangle, which is D plus E. So you got to be careful here because D plus E was representing the entire hypotenuse, those two pieces added together. Well, I have a similar relationship when I look at the medium triangle. If I compare E to C, and then I come back and compare C, the hypotenuse, to the hypotenuse d plus e, I get another geometric mean, and both of them use d plus e. So if you look at these parts, the main part we're interested in here is this d plus e is the hypotenuse of the original big triangle that I started with. And A was a leg of that triangle, and so was C. So when you read this next theorem, what it's saying is the leg of the right triangle, whether it's A or C, is the geometric mean of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Or as I say it, the leg squared is always going to be equal to the part that it touches and the entire hypotenuse. So let's look down here at a clearer picture where you have all that drawn out. So when you draw that altitude, again, you created two pieces, D and E. But now we're looking at the legs. Leg A is the geometric mean of the part that it's connected to, D, and the entire hypotenuse, D plus E. So we could say A squared should equal the part that it touches, D, times the whole thing, D plus E. Now the other leg shares that same relationship. C is a leg, so C squared should equal the part that it touches, which in this case is E, multiplied by the entire hypotenuse, D plus E. Practice these examples in your workbook, and let me take you through one of them, which is on page 7 of your workbook. And it's problem number 12. In problem number 12, you're given a couple numbers. It says JM is 3 and JL is 6. We're supposed to find MK, I'll call it X, and LM, I'll call that Y. Here's what the theorem says. It says the leg squared should equal the part that it touches multiplied by the entire hypotenuse. So again, let me color in the sides we're talking about. There's one part of the hypotenuse. There's the second part of the hypotenuse. And then the entire hypotenuse would be from J to K. So in this case, 6 is the leg, and it's next to the 3. So the equation is going to say the leg squared should equal the part that it's connected to, 3, multiplied by the entire hypotenuse. Now this, I don't have the whole hypotenuse, but I could say that the whole hypotenuse is just the sum of the two parts, 3 and x. So I could say 6 squared equals 3 times 3 plus x. Make it so we can see that a little bit better. And now this equation I can solve. So I'm going to get 36 is equal to 9 plus 3x. But when I subtract the 9 from both sides, I get 27 equals 3x. So x must be equal to 3. I'm sorry, 9, not 3. 27 divided by 3 is going to be 9. And x is what we called mk. So now if I need to find y, I could do a Pythagorean theorem, but I'm going to use that altitude theorem that we came up with to find y. Y is the altitude of the triangle, and the theorem says the altitude squared should equal the two parts that it created, 3 and x, multiplied together. But now we know that x is 9, so y squared equals 3 times 9, so y squared equals, I'm sorry, not y squared, y equals the square root of 27, which is equal to 3 root 3. And that's a perfect example of how we're going to use those two theorems to answer a question like number 12. So try the rest and see if you have any questions. Good luck.